Okay, so yesterday we dealt with a new idea of looking at force, so things that cause motion to happen in the first place. And today we're just going to extend that same idea. We're still going to deal with some free body diagrams, but now we're adding some numbers to it in real life situations. And what can we do with those numbers, and what do those numbers tell us? So the first definition we need to understand is, what is net force? So you saw from the free body diagrams we looked at yesterday that we were able to draw numerous forces acting on an object depending on what situation that object was in. Net force, net just means the sum of all of those forces. So if we have a bunch of different forces, we can take, if we have values for them, we can figure out what the net overall force on this object is. And that tells us a little bit about the way that it's going to end up moving or continuing to move. And so in order for us to do that, we have directions that we're giving here. So it could be left, right, north, south, east, west, up, down. And we just want to define what those mean in math. So if we're starting to apply numbers to them, we need to know, what do those directions tell us in terms of the math. So we should start out first by looking at, and this is pretty standard the way that it goes. So if we think about a compass rose, we can use this in a number of different ways. We can do the classic north, south, east, west, which we'll start off with. So the first thing we can do is call this north. This can be east, south, and west. Now, if we equate this to a number line, let's say if we were to think about this as a graph, this actually tells us a little bit about what's going to happen to the numbers when we're dealing with things in these certain directions. So generally speaking, anything in the east direction is a positive number. And if we're going opposite of east, so these should have little arrows on them. If we're going opposite of east, our numbers can still get big, but they're in the negative direction. So we'll put that here. Usually a negative number in this direction on a number line. And up on a graph, if you picture, is usually positive. And down on a graph is usually negative. And so in physics, we generally stick with this idea. If we're going east, it's positive, north is positive, west and south are negative. And if you forget that, you just have to think about what a graph normally looks like. Now, just to add to the confusion, sometimes it won't be north, south, east, west. Maybe it'll be up, down, left, right. So let's add those in as well. So up will also be positive. To the right will be positive. Down will be negative. And to the left is negative. So one other way you might see as well is, so north, south, east, west, up, down, right, left. I think that's it actually. Just so these are the ones you kind of have to remember. You might see forward, backward. All you have to really keep in mind, depending on what units they're using, is that if you're going in one direction, the opposite of that exact same direction, so a 180-degree turn, is a negative sign. That's all you have to remember. Okay? So what we're doing when we think of finding net force, okay, so the first thing we're going to look at is the symbol that we use to represent it. So net force is, remember, force is a capital F. It's a vector quantity, so we put the arrow, and we usually just in small letters write the word net as subscripts. Okay, so if we're trying to find the net force on an object, really what we're doing is we're just adding up all the individual forces in a right-left direction or an up-down direction. So we just take each individual force and we continue adding them to figure out what the overall net force is. And so depending on how many forces you have, this can keep going on and on. So let's look at an example, because you know in some of your diagrams from yesterday that you end up with some up-down forces and some left-right forces. Now, we're not going to get into actually combining them. We're just going to deal with things that are happening vertically and things that are happening horizontally. So let's look at an example. So a sled with two kids is being pulled forward. So here's the first motion or force in the snow with a force of 15 newtons forward. Okay, and the force of friction, so here's another force, and remember friction always acts in the opposite direction, is 6 Newton backward. And we've got some up-down forces. We have the force of gravity acting on them. So force of gravity is a third force, and it's 525 newtons. So what they want us to do is draw the free body diagram. So recall that our object, which is our sled, is represented by a point, and we use vector lines to represent all of our forces. So our first force was forward, so we'll make that to the right. Remember, it doesn't matter which forward it is. It could have been forward this way, but we have to know that our friction is just going to oppose that. It's going to go in the opposite direction. And we have also been told about a force of gravity, and gravity always works straight down. So here's our three forces they tell us about. Now, if we label them, I'll label them matching colors. So our first one was our forward force of 15 newtons in the snow. So we could call this our applied force, and it's equal to 15 newtons. And friction, which is in the opposite direction, is F, and it's equal to 6 newtons. And our final force in green here is gravity, Fg, and it's equal to 525 newtons. Now, there's one extra force here that they're not telling you about, but we are expecting you to know at this point. Remember that force I told you about, that if any object is ever resting on anything else, in this case the sled is resting on the snow or on the ground, we have that normal force. So even though they don't tell you, you have to get in the habit of knowing if something's resting on the ground, it's because gravity's pulling it. Why isn't it falling through the ground? Because there's this equal and opposite force called the normal force. So we just have to keep that in mind, that anytime we are dealing with any object that's on the ground, this normal force will be balancing our gravity. So therefore, they don't tell us a number, but if it's balancing gravity in the opposite direction, we know that it's going to be 525 newtons in the up direction. So now, what they want us to do is find the net force. Well, we're going to start off by looking at it in both directions. So remember I said we're going to just break it down into vertical, what's happening vertically, and what's happening horizontally. So let's start with vertically. What's happening vertically? And we'll call that the y direction. So our net force in the y direction, so vertical, is equal to a positive, remember up is positive, so positive 525 and plus, because it's the sum of all of these, but because it's in the down direction, it's a negative 525. And which works out to really our positive value of the up direction, our normal force, minus our gravity force down. And this makes sense because if this sled is stationary, vertically stationary, it's not moving up or moving down, it's just on the snow surface, then these have to be balanced, meaning that our net force is 0. A net force of 0 means you're not moving in that direction. So right now we're just looking at what's happening vertically, and these guys are the exact same numbers. So vertically, we know the sled is not moving up, nor is it moving down, it's resting on that surface. Now, let's deal with what's happening in the x direction or horizontal direction. So we have a net force for the x direction or horizontal, And we start out with what's happening in the positive direction. So we have 15 newtons to the right. And our friction always works in the opposite direction. So we're subtracting that. 6 newtons to the left. 15 minus 6, we end up with positive 9 newtons. And that's in the forward direction. We chose this as our forward direction. So the net force for this sled is 9 newtons in the forward direction. Okay, so we're going to look at one more example together as well, where just one extra calculation involved here. So a ball with a mass of 2 kilograms is falling through the air towards the ground downward. If the force of air resistance is 10 newtons, draw a free body diagram and determine the net force on the ball. So let's start with always start with the free body diagram because it might help you to visualize what's happening. So here's our ball. And we have the force of gravity which is pulling it down. And they're telling us that there's air resistance in the up direction. So we've got two vectors here. Our force of gravity, which we don't necessarily know yet, but they tell us our air resistance, which we can consider friction, right? It's working against it, is 10 newtons. But the extra piece of information that they give us is this. The mass of the ball is 2 kilograms. Remember yesterday's note, we dealt with the difference between mass and weight. And if we want to know the weight of something, it's also the same as saying the force of gravity on that mass. So even though they don't tell us the gravity force, because we have the ball's mass, we can calculate what that gravity force is. So add that to your diagram anytime you're given information about this. So the mass of the ball is 2 kilograms. And therefore, we can automatically figure out what the force of gravity is. Remember, it's your mass, so 2, times the acceleration due to gravity, which is that constant value, 9.8. So we end up with 9.8 times 2. We end up with 19.6 newtons in the down direction. So this ball is falling through the air with this force. The force of friction or the air resistance against it is 10 newtons. So now we can write a net statement for what's happening vertically. So vertically is the y direction if we think about our graphs. And we have a positive up, we'll call this up, positive up, so of 10 newtons positive, minus, because we're in the down direction, minus our gravity, which is 19.6. And so what we end up with is negative 9.6 newtons. So what does this negative sign mean when we're saying that our net force is negative 9.6 newtons? You can leave your answer like this, but because this is a vector quantity, we should turn this into what this negative sign means. And this means, so you can have either or. If it's a negative force, it just means that it's 9.6 newtons in the negative direction, which in this case is down. So either of these answers is fine because that negative sign tells us the direction, but you could translate that into what that actual direction is.